Alright, we are going to do something different. We are going to do a problem that is not in Fallen or really in any textbook, but a problem that I had to do on an exam. And so it's just something that would be good for me to go through, and it is loosely based on one of the exercises in Fallen, so it's probably good to go through. And it is kind of an interesting problem. The particular problem, I think it's like either exercise 15 or 20 in chapter 8, something like that. But in Fallen's version, he actually, like here, it's easy to work out an explicit formula for this VK here. He actually starts with what the formula is and tells you to prove things about it, and you get all these facts. But here we're kind of not worrying too much about the specific functions themselves, but rather on the properties. And so this is really an exercise of understanding how Fourier analysis works. So we're going to start with part A. Parts A and C are pretty quick, and B takes a little time. So let's start with A. See here. So let U be an H. Then U times the indicator of the closed interval from 0 to 1 is equal to U almost everywhere. Why is it not equal everywhere? Right, yeah, because let's see here, U equals 0. Right, so got 0 and 1 here. So basically U is going to be 0 here. Yeah, it doesn't really matter. The only reason we're introducing this indicator function is to make it easier for us to use things that we already know. Because what can we do from here? We can do so, not mu, but then U1 is equal to U times the indicator of 0, 1. That's because they're equal almost everywhere. And this is less than or equal to U2 times the indicator of 0, 1, 2. And this is by Holder's inequality. But what is that? Well, the 2 norm of this indicator function is just 1, so this is just U2, and that's finite. And so thus, H is in L1R because for every single U in H, U is in L1 of R. So now for part B. This is a little tricky just because you have to kind of dance around between when you're taking the Fourier transform, like when you're dealing with things on R and when you're dealing with things on the torus. So anyways, given F and H and G, which is F hat, let Fn equal sum from k equals minus n to n F hat k uk. So if the UKs were actually replaced, if the UKs were replaced with e to the 2 pi I kx everywhere, then this would just be, then this would look just like the partial, there's a word for it, I forget, but this very much looks like a Fourier analysis thing basically. So let Fn be this. Then clearly Fn is an H. Why is that? It's because it's just a linear combination of the UKs, and the UKs are an H, which is easy to see. Well, just by definition, actually. So that's in here. And Fn hat is equal to the sum from k equals minus 1 to n. The F hat k's are scalars here, so they come out. But we put the hats on the k's. But this is just Gn by definition. Because UK hat is equal to VK. So that's that. Let phi be the one periodic function on R such that phi restricted to interval from 0 to 1 equals f restricted to 0 to 1. Or phi equals f on 0, 1. So you basically take what f is on 0, 1 and you extend it periodically. And we're going to let phi n be the actual nth partial sum of the Fourier series phi hat k ek. Then fn equals phi n on 0, 1. And why is that? That's because on 0, 1, let's see here. On 0, 1, UK hat is equal, no, Fn. UK here is equal to E sub k on 0, 1. And in terms of phi hat and f hat is, when you actually write out f hat, the only part of the integral that's the integral that defines the Fourier transform is taken over all of R, but because f is positive only on the half-open interval from 0 to 1, you just take the integral on 0, 1, and you get, and so it becomes the integral from 0 to 1 of f times e to the minus 2 pi I kx. And then as for phi here is a one periodic function. So when we take the Fourier transform, we treat it as a function, as like the Fourier transform on functions on the torus. And so it's the integral that defines its Fourier transform is defined to be from 0 to 1 of phi of k, or however it goes. But yeah, because phi and f are the same on 0, 1, they agree. So fn equals phi n on half-open interval from 0 to 1. Therefore, the 2 norm of f minus fn, well, let's actually write this out. This is integral from 0 to 1 of f minus fn squared d, I'll just say m. I don't really care what measure we have on here. But that is equal to, because we're on 0 to 1, this is equal to phi. And this goes to 0, since we know that phi n goes to phi in L2 on the torus tau, where we take tau equal r mod interval from 0 to 1, basically. So, thus, fn goes to f in L2 of R. Because, of course, this 2 norm is in R, and this 2 norm is on the torus. So fn goes to f in L2R. F and fn are in H. So f minus fn is in H. So by part A, f minus fn, the 1 norm is less than or equal to the 2 norm. Also, for each h in L1 of R, it is easy to see that integral of h u is the uniform norm of h hat is less than or equal to the 1 norm of h. And to see this, you just write out what the integral of defining h hat is, and you just evaluate it at some value, and then you just take the absolute values inside, and the e to the minus 2 pi I whatever drops out because it has norm 1, and what you're left with is just the integral of the norm of h, which is h1. And this upper bound will hold for every single point where you evaluate h hat at, and so the uniform norm is less than or equal to h1. It's a kind of a standard fact in Fourier analysis. Hence, g minus gn uniform norm. Well, g is f hat, and gn is just fn hat, and so hats are linear, so you can just pull them out. So this is this uniform norm, which we now know is less than or equal to f minus fn1 by the previous result, and then this, by the result before that, is less than or equal to f minus fn2, and by the result before that, this goes to 0. So hence, gn goes to g uniformly, which is precisely what we mean when we conclude that the difference of g with g, the uniform norm of the difference, tends to 0. So that finishes part B, and then part C, I'm only going to scroll down a little bit because we don't need much. By Plancherel's theorem, and since Fn goes to F in L2, we have g minus gn, the 2 norm here. This again, we pull out the hat. This is f minus fn hat 2. But by Plancherel, this is f minus fn of 2, because Plancherel tells us that the Fourier-Plancherel transform, which is basically the Fourier transform extended into L2, and you might have to do some stuff there, but it's basically the Fourier transform in L2. It's an isometry, so it preserves the L2 norm. And this, we know, goes to 0, because Fn goes to F in L2, and hence, Gn goes to G in L2R. And this completes the proof.